Hi, everyone. My name is Travis Rector, and I'm a professor of physics and astronomy at the University of Alaska Anchorage. And I'm also one of the organizers of a group called Astronomers for Planet Earth. And this is part of our webinar series where we invite scientists and other people to come on line to tell us about the work they do and how it pertains to climate change. And our guest today is Dr. David Grinspoon, a good friend of mine from way back at the University of Colorado. He's now at the Planetary Science Institute, and he's an expert on a variety of things, including astrobiology, in particular, the atmospheres of the terrestrial planets. And so if you have not done so already, David gave an awesome meta talk about the things he talks about when he talks about the atmospheres of the different terrestrial planets. And that, if you haven't watched it, the link is on YouTube and you can check that out. But what we're going to do today, and this is being recorded, is we're going to go through the questions that people have submitted after watching that talk. And so what I wanted to do is, first of all, thank you, David, for joining us today. And looking at the comments and things that people have asked about, and this is an experience I've had all the time. It seems like whenever I teach about the atmosphere of Venus and this raging hell that it is, the first question I always get from my students is this what's going to happen to the Earth? Is this what climate change is going to do to us? So, David, I guess our first question for you is and Chris Masner asked this question, is the Earth vulnerable to a Venus-like runaway? Are we going to turn into Venus someday?
Yeah, it's a great question, and it is a common question. And there are a couple different ways to answer it. And by the way, thank you very much for inviting me to do this. And I think it's great. Astronomers for Planet Earth is just is a wonderful organization and concept. And by the way, it occurs to me that if I end up giving a talk about this experience, then that would be a meta talk. Which, oh my God, I'm going to blow my mind if I think about it. But yeah, no, there's a couple different ways to answer it. Because if you think of the long-term fate of Earth, the sort of inexorable fate of Earth as the sun evolves, we do picture a Venus-like state happening eventually. So you can say, yes, this is likely to be the fate of Earth, but on a very long time scale and not as a result of our own inadvertent machinations of the climate. On a shorter time scale, it's not likely, and this is something. It is kind of a common misconception, and I sort of alluded to this in my talk that that the climate lesson of Venus should be like, look at all that CO2, and oh no, we're going to turn Earth into Venus, which makes it makes kind of a neat, scary parable, but isn't strictly likely if you actually look at the mechanics of the atmosphere. And again, one needs to quickly add, I'm not downplaying the risks of climate change when I say this, where we could change the Earth in such a way that it is really incompatible with certainly our civilization, if not our species, but without actually even getting close to triggering a runaway greenhouse. So there are danger points that are much closer, but the actual triggering of a Venus runaway is an extreme state that we're just not in danger of. And part of the reason I think, or at least one contributing factor to the common misconception about this was a little unfortunate. James Hansen, who is a very well-known climate scientist and has done great work and is one of the people who's like sort of legitimately on the boundary between planetary atmospheres and terrestrial atmospheres. And he's most famous for sort of sounding the alarm in congressional testimony in, I guess it was the late 1980s, saying this is real and it's happening and we have to take it seriously. And he's been very much an activist as well as a publishing atmospheric scientist. And he's great. I'm an admirer of his and he's a friend of mine, but he wrote a book. There's a book he wrote, a popular book called Storms of My Grandchildren, which was just sort of summing up of his warning about climate change. And it's a very good book, but there's a section in that book called The Venus Syndrome, where he makes the statement, he talks about the runaway greenhouse on Venus, and he makes the statement that, you know, if we burned all our fossil fuels, we could push Earth over the threshold and it could become like Venus. And, you know, we've actually had a lot of conversations with him, and he came, we've had a series of meetings of comparative planetary climatology that I helped organize, and that Jim came to the first one, and we had a long discussion about this, and he kind of walked that back. He was like, he sort of admitted he had been using that for rhetorical purposes, not because he kind of believed it at the time, but he hadn't really gone through. If you actually go through the math and look at the feedbacks, and a lot of it has to do with cloud feedback, it's not as simple as just saying, let's add lots of CO2 to Earth and it suddenly turns into Venus. It's a different situation because Earth gets half the solar radiation that Venus gets. And when you add in cloud feedbacks and the presence of the ocean and everything, it's very, very hard to push Earth into a Venus state with the current level of solar insolation. If you're talking a couple billion years in the future, then it's different. So I tend to, so in the answers I give, I tend to say, we're not going to turn Earth into Venus, but we are in danger of pushing Earth into a state which is very dangerous for us. And that is an accurate long-term projection of terrestrial evolution. It's just that's not, it's a little too simple to just say, if we put in this much CO2, it's going to suddenly instigate a runaway greenhouse where the oceans are going to start to boil off. That's not really an accurate projection based on what we know.
I think that's a really important distinction, especially when people talk about, you know, saving the Earth. We must save the Earth. Well, we're not going to destroy the Earth, and we're not even going to, you know, like boil away the oceans or anything like that. What we really are concerned here is saving humans and the animals and plants and species that we rely upon. And so for those of us who teach climate change, that's something that I think is really important to emphasize, is that it's really only been the last 10,000 years or so that the Earth has been habitable in the way that we inhabit it now, as far as our agricultural needs and whatnot. And so I think that's a really important point, is no, we're not going to create a Venus, but we could make things really, really uncomfortable for humans and the things we rely on. So thank you for that, Dave. So another question that
I see
several
a hand
people
up from Chris.
Is there a hand up? Okay, go ahead, Chris.
Hi, it's a real hand, at least here, not a virtual hand.
Oh,
Sorry.
okay. I didn't see I can't see everyone at once. So
Oh, that's okay.
For those of you who are present, if you want to use the virtual hand, that'll help me to.
All right, I'll try to find that on my thing. But I'm just a little concerned about sort of weakening the message and the object lesson of Venus. So maybe we can find a middle ground and say something like, human actions could turn Earth into as much of a hell as you want it to be, or as such will be such a hellish place that life on Earth as we know it will be impossible long before we get anywhere near what Venus looks like today.
Yeah, no, you're absolutely right. I mean, I was sort of paraphrasing an answer just now, but I think you're right. It's very important to draw that contrast, but then also state emphatically that we are talking about very, very dangerous changes. And that we're not saying, oh, so don't worry about it. That's not the message. The message is it's a different kind of transformation, but we are in danger. We're certainly in danger of, for one thing, we're pushing Earth in the direction of Venus, even if we're not in danger of reaching that threshold. For another thing, we don't have to go very far in that direction until it becomes very, very, it becomes disastrous for our attempts to have a global civilization.
Like, for example, I don't know if you could answer this, but let's say the CO2 level gets up to 1,000 parts per million. Could we have agriculture as we know it today on Earth? Would that just be gone? We know, like, almost all growing land would just be, would turn to a desert or something like that. I mean,
yeah, I mean, that's
some kind of statement, at least along those lines, approximately.
Yeah, that's an interesting question, and I cannot rigorously, give you a quantitative answer based on that. But certainly, you're talking about a planet with much less agricultural, much less surface area where one could grow crops. Whether or not it's zero, you're beyond the point where you could support anything like the current human population.
Okay.
So you're talking about a collapse at that point. Whether or not it's down to zero, I'm not sure.
Yeah, sure. So we could throw in a phrase like billions of people starving to death, and that would be pretty hellish enough. So I think that would get across the point just fine. Thanks.
Absolutely. And then, the other thing I say, because I also don't want to give the impression when I'm having that discussion that so then we don't have to worry about thinking about Venus for this, is that the value of studying the climate of Venus and its evolution is that it's a laboratory for testing out and really understanding if we know how to model climate, and learning about the pieces of climate models that are essential, cloud feedbacks, because it's a very different situation than the situation here on Earth. It protects us from the phenomena that some people worry about, that our models are sort of tuned, not even intentionally, to only handle a narrow set of situations close to what we see today. And so by having completely different examples of planets with the same physics, but really different setups in terms of atmospheres and clouds and so forth, it allows us to sort of check our honesty and become more sophisticated about how these tools that we depend upon, these climate models, work. So it's really valuable in learning about climate change on Earth, just not in the simplistic way that we're about to turn Earth into an exact copy of Venus.
So I see Bill and Adrian both have their hands up. Bill, your question was the next one I was going to ask, but go ahead if you have a question you'd like to ask now.
Yeah, I guess it's more of a comment on this. I mean, Venus obviously is such an extreme case with surface temperature of 700, 800 Celsius, whatever it is. When I've given public talks, I've had a hard time coming up with a good way to make a degree or two global temperature change sound significant to the public. And I wondered if David had, been able to address that in his public talks in a way that would help us communicate that these, what sound like small changes, are really immense changes in our global system at 1 or 2 degrees or a few degrees now, projecting into the future a little bit. But so, David?
Yeah, now that's a very good question, and it is a challenge, because we describe these numbers that sound small and therefore they must be innocuous. So 2 degrees, what's the big deal? But I think that one thing that helps is you start talking about the predictable consequences, and you say, well, imagine an Earth without sea ice. And you do talk about the predictable changes in agriculture and the monsoon in Southeast Asia, and these 2 degrees doesn't sound like much, but when we run our models with 2 degrees, here's what happens, and it's a really changed planet, and one that we would not be able to have the kind of civilization we have, or that we're trying to have right now. So yeah, you do have to sort of temper those seemingly small numbers with some specific examples to make sure that people's imagination don't sort of get filtered out by what sounds like a small change.
And following on that, how much warming would it take to melt all the sea ice?
If I've seen a few different estimates of this, but this is one of the big differences between, you see this range of IPCC scenarios, and there's the scary, 7 degree scenarios, and the slightly less scary 1.5 degrees. And it's in that range. I mean, the disappearance of the sea ice is one of the sort of large scale phenomena that we have within our power to hopefully prevent. But if the worst case scenarios that are possible, given those projections that that we're used to looking at, include potentially complete loss of the the seasonal sea ice.
So maybe 10 degrees warming could do it. Okay.
Yeah, I think 10 definitely does. I think a little bit less.
Okay, so if 10 degrees melts all ice on Earth, then 2 degrees is sounds a lot more impressive.
Right. No, that's a good way. That's a good way to talk about it, I think.
I just want to point out, as Brian mentioned in the chat, it's warming is exaggerated towards the poles. And so if you have ice at the poles, I'm surprised that the number would be as high as 10.
I think it's considerably lower than that.
It's lower than that. I mean, by 10, there's no question. And there's a little bit of uncertainty in what the exact number is, because this is a complex phenomenon. We're not just talking about an equilibrium calculation here. We're talking about, motion, ocean circulation and dynamics. And, there's a lot of details that actually factor into what exactly the number is.
But
if I remember correctly, I mean, by 4 degrees Celsius, you're pretty much guaranteed ice-free summers. And so, I mean, that's obviously well below 10. I wanted to give everyone a chance to comment and ask questions. Adrian, you've had your hand up for a while, so I wanted to.
Oh, this is kind of a follow-on to some of these conversations, and also to something that, David, you said toward the end of your meta talk, which I thought was really important and interesting, which is that the uncertainties that you see in the projections of what the climate could be on Earth, that the dominant uncertainty in those is not uncertainty in the climate models themselves, but in what human behavior will be. And I thought that was a really important point, and sort of connected also to your point of that Venus and Mars provide places for us to sort of test our models and see if the models are good. I think it would be really useful and helpful to have really good, graphics, and maybe these exist, and probably these exist, and I don't know what they are, of like showing how good the models are, like how well we can predict these things, like that sort of establishing that as part of a public talk seems a really important thing to do before, even talking about the range that might happen, depend on what people do, just giving people.
Yeah, that's a good idea. A model versus data on some of these other planets, and how we really are able to, at least the simple aspects of the problem. The evolutionary aspects are harder, but
exactly. I get that.
The current climate state is, the current
right.
Climate state, we can pretty much, from first principles, say, give me a planet with this mass, this much atmosphere, roughly this amount of cloudiness, and these other parameters, and model its climate, and here's the temperature profile, and then here's the data temperature profile, and it looks the same. So that is powerful. That's right.
We could. It would be super helpful to have a set, a few slides that showed that, and that anybody.
That's a good idea.
Could use.
I have some of that, but it would be good to compile it in such a form that it was specifically designed to illustrate just what you're saying.
Cool.
So, so related to that, so Bill had posed the question. I think we've already answered it as far as like, how much can we trust the models? And it seems like that, the dominant factor in the uncertainty is human behavior. That, there are still uncertainties in other parameters, but what people decide to do far outweighs any other uncertainties. Is that a valid statement? Is that?
Yeah. There are some uncertainties for sure remaining. Some of the largest ones have to do with clouds. Which are, just tricky and can force either way, depending on what altitude they are and what, the specific details of the clouds. That's been a sticky point. And there are a few other physical unknowns in terms of various feedbacks and so forth that create some uncertainty. But when you look at that big dispersion, those famous graphs showing all the different IPCC scenarios, by far the biggest difference between the high scary ones and the lower less scary ones is, whether they call it business as usual, or, they have these different they're sort of cartoon projections of what humans are going to do, very simplified. And that's the major uncertainty is, do we change our global energy system? That's really the big one. And then there are, other ones about agriculture and so forth. But collectively, those are the big uncertainties.
Yeah, so there's a couple comments here that I wanted to address that were put in the chats. Julie brings up a very good point, and that is, and we were talking earlier about, saving the Earth and are we going to destroy the Earth? And she mentions that she was talking with a group of kids, grade 9 kids, and one of them said, is it true if we don't take care of the Earth, it's going to blow up? And this is horrible to think that our poor kids are afraid at this level. But I think it brings up a really important point as to what visuals we can evoke when we say certain things. So if we say the Earth is going to destroy it, you can imagine a Death Star-like scenario, and Han Solo and Great Shot Kid and all that stuff. And so I'll relate a similar story. This was more than a year ago at this point, but one night my daughter came in. She woke up and she said she couldn't sleep because she was worried about drowning. And I asked her, well, why are you worried about that? And she said, well, I heard the oceans are going to rise up, and won't we all drown? And so, I had to explain to her, how much the ocean is going to rise and why our house is not at risk of being submerged. And so both of these are interesting examples, I think, of what visuals we evoke when we say certain things. We need to be mindful of how they might be interpreted, especially amongst young audiences. Okay, so I wanted to move on to questions.
Yeah, just a quick point about that. I mean, the phrase saving the earth is such a powerful emotional statement. And I don't dislike it really as a statement because it is powerful, but we have to make sure that people understand what we mean. We're not literally talking about the earth is going to disappear. Just like Pluto didn't disappear when we said it wasn't a planet anymore. It's still there, but it just simply, when we say save the earth, we mean preserve what we think of as preserve the environment, that the planet we love the way it is. The things we love about it are at risk, and so you just have to say that that's what we mean. We're not literally talking about something happening to the earth, and we're not talking about all life on earth dying out,
right?
Which is another thing people sometimes think. We're probably not even talking, if we really get down to it, about the human species dying out, but we are talking about the collapse of sort of everything we care about, and that's pretty major. There's a way to describe it in terms that are sufficiently concerning, but are not sort of hyperbolic.
Yeah, and that connects to a point that Chris makes in the chat, and that is, that people can be disconnected to the things we say. Like if we talk about all the sea ice melting, well, I mean, unless you live in the Arctic like I do, or subarctic, you probably don't care. I mean, why should I? If you live in Florida, why do I care about the sea ice melting? And so the key thing here is you always need to connect what you're talking about to something that people do care about. And so if you live in a coastal region, or if you're on a Pacific island, then yeah, maybe you're going to care about sea level rising, or maybe you'll care about things that other people don't. And so that's a key message for everyone is to always explain the consequences of climate change on a local basis.
Sorry, Travis, can I just ask, since it's come up several times, when we're referring to sea ice, we literally are talking about the ice that's, say, up in the Arctic. We're not talking about the ice that's on Antarctica or Greenland.
Well, so I mean, Antarctica and Greenland are land ice, and in the Arctic is sea ice, and it is important to distinguish between the two. The melting of sea ice is not going to impact ocean levels, though it will certainly impact the albedo of the Earth and cause warming to accelerate. Dave, do you want to expand on that?
No, yeah, I mean, what you said is absolutely right. And that's, some of the discussion earlier about, what the magic temperature is. A little bit it depends on, because there is the possibility of really an ice-free Earth. But that's a much more extreme state than just the destruction of the sea ice is concerning. It does not, as Travis said, it's not directly related to sea level rise, anything that's floating. And that is another little physics lesson that can be worked into these discussions of why that is, the ice cube in the glass of water. The loss of the sea ice is concerning for a lot of reasons. And one is because of the ice albedo effects, which and ice albedo is a good, if you want to talk about feedbacks, which is, depending on how long a discussion you're having, it's kind of a good next level thing to really start talking about. And that's one that's just easy to understand. If a planet has an ice cap, it's reflecting and keeping itself cool. If it doesn't, if you warm a planet up to the point where it's really losing its ice, then it also is losing its ability to cool and maintain its ice. And that's, it's just a good example of a feedback. But yeah, that, at 3 or 4 degrees, we're in danger of losing the sea ice. At, over 10 degrees, we're in danger of actually pushing Earth to really an ice-free state, which is a state that it's been in many times. And this is another interesting thing when you talk about long-term climate history, but then you also have to press home to people that you're talking about states of the planet that our civilization would not, be able to exist on.
So related to that, a couple people have asked about tipping points. Adrian asked in particular about the carbon thermostat and how that's affected by sea ice. And so can you elaborate on, what tipping points are, how close we are to some of them, and what that means? I mean, when people say, you hear this all the time, just the defeatism of where it's a point of we're already past the point of no return. So how do you counter that? How do you respond?
Yeah, that defeatism is one of the really tricky aspects of this whole conversation, this whole issue. Because it's tricky. You want people to be concerned. And in general, you want a lot of people to be a little bit more concerned than they are now, and have it like really affect how they vote and their lifestyle choices and all that. But you got to be careful, because if our relentless messages, everybody needs to be more and more and more concerned, then it's easy to, there's a human tipping point too, right? There are tipping points in human psychology and politics and dynamics, and you don't want the overriding sentiment to be like defeatism. We're screwed. There's nothing we can do. It's too late, right? So that's really tricky. And related to that is this perception that there are such things as tipping points, and some of them we don't know how close they are, and that's part of the reason why you don't want to go near the top of that envelope of uncertainty, not just because of the directly predictable consequences, but because with some of these possible tipping points, we don't know how close we are to really setting off. And one example of that is the methane release from from the seafloor in some of these polar regions. That it's not clear how much methane and how easy it is to start triggering the release in some of these polar terrains. And most of the people, and one sees a lot of alarmism about this, and most of the people I know that actually work on that, and you talk to them and you say, well, we're probably not actually that close to a tipping point, but I can't say for sure. And it's that can't say for sure that makes us, it makes it really dumb you don't want to run that experiment. So there's a corollary to all these tipping points that you can give a few examples of. The methane is a really good one, that it's very hard. The systems are so complex, it's very hard to say exactly where those tipping points are. And that's where the precautionary principle comes in. You don't want to run an experiment where even a very low probability outcome is the destruction of your world, essentially. So if you don't know the exact location of the tipping point, and if the stakes are as high as they are, then the smart policy is to not come close to those possible boundaries.
I have a metaphor we can use for that defeatism issue, because I've faced it many times too. And I think people would like to cop out by saying, oh, I don't know what to do. I don't know what to do. I don't know what to do. Oh, now it's too late for me to do anything. So that's kind of a cop out, but a lot of people want to do that. So what I say, oh, and by the way, people kind of have, from movies or whatever, they have a mindset that everything's fine, everything's fine. Oh, and now everything's terrible, or everything's bad, and now we blow up the Death Star and everything's fine. And it doesn't work that way. It's gradual. Things just get gradually worse. So my metaphor is this. You have an infection in your fingertip. And is it too late? No, you could treat the infection. But if you don't treat the infection, then your fingertip is going to get gangrene and you're going to have to cut off your fingertip. Now, if you still don't treat it, then your whole hand is going to get infected and turn gangrene. You're going to cut off your hand. Is it too late? No, it's not too late, but you're going to lose your hand. Or it could be your arm, or it could be. So it's just a question of how much do you want to lose? That's what we're dealing with. As the climate worsens, we will lose more and more and more of our fisheries, of our agriculture, species, and so forth. So that's the metaphor I use, so that people can break the mindset of everything's bad until it gets good, or everything's good and then it's too bad.
Yeah, no, I think the sort of disease metaphor is really an excellent one. And I'll tell you a metaphor that I hear a lot that I really don't like, even though I'm an astronomer for planet Earth. People use a metaphor of an asteroid that's heading towards us, and it's as if scientists have identified this asteroid that's heading towards us and it's going to destroy everything, and people know about it, but they're just walking around oblivious to it instead of taking action. And that one hears that like, oh, it's an asteroid that's heading towards Earth, that metaphor a lot, but I really think it's a bad one, because it implies there's sort of a moment by which if you fix the problem, then it's fixed. And it's like with an asteroid, if you deflect it successfully, then it's not a problem anymore. It's a trajectory that, either is or isn't going to hit the Earth. Whereas with climate change, it's not a problem that there's a moment and you fixed it. It requires a long-term commitment to thinking in a different way about the way we interact with our environment. It's a very, very different kind of problem. It's not a momentary fix. It's a change in really our mindset about how we behave collectively and how we act as a society living on a planet.
So thank you, Dave. Brian Sound has had his hand up for a while, so I wanted to give him a chance. Brian, do you have a question or a comment?
Yeah, it was sort of a little bit back, but it's this general, topic about whether to, how to scare people, how to get people interested in this, that it's important without like scaring them. One thing that I'd like David's input on this, but one thing I like to point out is how sort of constant CO2 has been over the last 10,000 years, and that, ecosystems have kind of evolved and optimized to this equilibrium. And not only that, but we've set up our infrastructure, human infrastructure, around this temperature. And so moving everything out of equilibrium, we're moving from an optimal point. And so there's just no, a lot of people like to talk about, oh, maybe it'll benefit, changing things will benefit agriculture, benefit whatever, but it's like everything has been optimized over thousands of years, both natural ecosystems and human infrastructure. And I just, taking us away from that equilibrium is a problem.
Yeah, that's a good point. And it's also good, that perspective helps in countering another point which one hears, which is that, well, if you look on longer time scales, CO2 has been much higher. It's been 1,000, or it's been much lower. And Earth has had all kinds of climate changes. It's had ice ages, and, this is natural. And life didn't go extinct, and, which is all true. But as you say, Brian, we've optimized to take advantage of these conditions that have obtained over the last 10,000 years. And actually, we've made ourselves very fragile and very vulnerable, in a sense, to minor changes that life has accommodated to before. And in a way, we're much more fragile now than when we were hunter-gatherers, because we've settled down in cities. We've populated all the coastal area, most of the coastal areas of Earth. So we've made ourselves dependent on sea level being within a very narrow range. It's not easy for us to pick up and move like we did when we were hunter-gatherers and conditions changed. And we've also maxed out, to a large degree, the carrying capacity of the planet in terms of, if there are, later this century, there are going to be 10 billion of us, and the margins by which we can feed all those people using the the land that we have available are small and depend upon a range of conditions that we've accommodated to. So while it's true that life can adapt to a much wider range of conditions, it's not true that our what we've built, this hugely populated, coastally inhabiting, agriculturally maxed out civilization can accommodate to those changes.
I'm far from an expert on this, but it seems like, I have my farmer friends talk about just, the incredible advances they've made in the production yield of their land over the last 50 years or so as technology has improved and do that. But what's become clear is we really are maxing out what the Earth can do. And we already have the dilemma of trying to sustain over 7 billion people on, on the Earth. And now you throw this into it, you throw climate change into it, and you're taking a system that is already at its limits, and then you're going to make things much worse. Catherine Hayhoe has a line that I really think is good, and that is about the threat multiplier, that climate change can take existing problems and just make them that much worse. And so it didn't necessarily create the problem, but it will make it worse. And so issues, whether it be, forest fires or crop failures or hurricanes, those are all problems that always existed, but now climate change has made those even worse.
That's right. And, that with the green revolution, we remarkably increased the production of, the average hectare of cultivated land by an incredible amount. And so we staved off the predictions, the Paul Ehrlich predictions in the 1960s of the population bomb, that there was going to be mass starvation. To a large extent, we are able to feed the people of the planet because we increased that productivity. But it's false to assume that can continue forever. And even if you could max it out further, you're starting to run into other limits, like the nitrogen cycle and just having enough water, to grow those crops. And, water is going to be a huge issue coming up. So that I think you're right, Travis, that, even if we haven't literally maxed out the carrying capacity, we're up against like several potential limits all sort of hitting at once. And it's folly to think that we can go further in that direction.
Okay, so a couple of the questions that we've had. Speaking of models, Sharon Morsink, who's here with us today, asked in the comments on YouTube about the role of the Earth's spin. Has modeling been used to study how the Earth's faster spin in the past, what effect that might have had on the climate, and was that a factor in the history of the Earth's the evolution of life on Earth?
Yeah, it's a great question, and actually, it's a question that has come into sharp relief recently because of new modeling that's been done on with exoplanets now, and this idea that there may be lots of variations of sort of Earth-like planets with where there's so many parameters one can vary and try to understand the climate evolution and the habitability of planets that are more or less Earth-like, but have, slightly different mass or slightly different distance from a star or spin is another one that people have been looking at more carefully now than they have in the past. And one thing that's come out of this is a very interesting result when you look at the difference between Earth and Venus. And this is something I'm still trying to wrap my head around, but it seems to be a robust result, which is that, for the first time, we now have the ability to really take a GCM, a general circulation model of the same kind that we use to model climate change on Earth, and really adopt it for other planets and other sets of planetary parameters. It's sort of a hard thing to do, harder than you'd think, because those models have so many. They're just very complex, and a lot of them they're sort of optimized for Earth in ways that they shouldn't be. And you learn about all that when you try to move it to another planet. But we finally have good GCM models for Venus, and people have taken a new crack at this question of why and when and how exactly did Venus go from what was apparently a more Earth-like climate when it first started off, based on some data we have, which isn't really that great, in which we need to shore up with future observations. But as far as we can tell, Venus started off with much more water than it has today. And we had this old idea that there was just a runaway greenhouse early on due to the feedback between water vapor opacity and surface temperature. And Venus lost its oceans, billions of years ago, and then has been different from Earth through most of its history. But in fact, these recent GCMs that have been successfully adapted and run for Venus produce a very different result. And what they suggest is that the oceans of Venus were much more stable than we thought, and persisted for a long time, and may have persisted for most of the history of Venus. I mean, they've clearly been gone for a billion years or so. We can tell that from the geological record, but earlier than that, we're not sure, and we have to rely on modeling and isotopic data and things like that. But the recent models point towards a much greater longevity of Earth-like conditions on a planet like Venus. And this is getting back to your question, because it turns out that it all hinges on rotation rate. That if you have a fast rotator like Earth in a Venus-like orbit, that what I just said is not true. It loses its oceans much more quickly. But the slow rotator hangs on to its oceans for much, much longer, billions of years longer. And the reason why is because of the effect of that slow rotation on oceanic and atmospheric circulation, and in particular on cloud dynamics. Because it turns out, and this was a completely surprising result, but it seems to be robust, that if you have a really slow rotator like Venus, that the dynamics are such that the clouds organize themselves globally in such a way as to almost ideally help to cool the planet and preserve the existence of a surface ocean, because the subsolar or substellar hemisphere gets sort of permanently cloudy, and the antistellar, or the night side hemisphere, gets permanently clear. The dynamics are such that the cloud, it stays cloudy on the day side and clear at the night side. And so for the same reason that, it gets, it cools off a lot more on a cloud-free night wherever you are than on a cloudy night. It's that night side hemisphere can really effectively radiate radiation, but the clouds act as a sunscreen on the day side. And if you speed up the rotation, this effect goes away. The dynamics are not like that anymore, and the planet will lose its water. So at least on a Venus-like planet, rotation rate it turns out to be critical to climate evolution and indeed to maintaining habitability. Now on Earth, as you say, that it was a much faster rotator in the past, and I know I've seen models, climate dynamic models, and I know there's interesting results about how it affects global precipitation patterns and erosion rates and weathering rates and so forth. I haven't seen any sort of simple conclusion, at least that I can recall, that it has some sort of dramatic directional effect, like that it would have made the climate much hotter or much colder because of that fast rotating early Earth. It's an interesting question, though. The results I can remember have to do more with sort of affecting precipitation patterns and so forth, and sort of more regional effects than some sort of secular global climate change that would have been a result of that rotation. Although it's a good question. I'm not exactly sure what the answer is.
So it's maybe more about the weather than the climate, maybe.
That I know it affects the weather dramatically, and it seems plausible that it could affect the climate. I just don't remember what the answer is.
Okay. Fascinating. Thanks.
So I mean, this is something that I was thinking about after your talk, and I mean, hearing that Venus once had more water kind of sent chills down my spine in a bad way, in the sense that now we have 3 planets in our solar system that at some point could have been life habitable. And now it seems like only one of them has somehow managed to avoid catastrophe, both Mars and Venus. Something happened, and now they no longer are, clearly supporting life. And so, and Leo Bircher had this question of, do catastrophic events like Snowball Earth, I mean, are these just events that, somehow the Earth just got lucky maybe and skirted its way through all these things that seem to inevitably happen? Could this possibly be an explanation for why, the Fermi paradox, why life is so rare? Are we just incredibly lucky we've avoided these sorts of catastrophes?
I mean, there are a couple different ways to look at it, almost like opposite ways you can interpret it. One is that, to some degree we have been lucky. There's permanent habitability is not guaranteed on any planet in our universe, right? I mean, even if your planet is fine, you could have a, you know, a nearby stellar explosion or something, right? You know, you guys know more about that than I do. There are, you know, nothing's guaranteed. And certainly, if you look at the most drastic extinction event in Earth history, the Permo-Triassic extinction 250 billion years ago, you know, one could imagine. I mean, if you have something that can wipe out, you know, more than 90% of the species on a planet, one can imagine that there, you know, that it's not impossible. You could have something that was worse than that maybe would have wiped out all life. But you know, it's interesting. The snowball Earth can, you know, you could use it as to argue the opposite point, that life on Earth is incredibly robust and has been able to survive even the most extreme examples. Because I mean, snowball Earth is an interesting thing to talk about, because on the one hand, Earth got completely frozen over, or, you know, maybe almost completely, depending on whose evidence you listen to. And by the way, it's a great example, again, if you're talking about feedbacks and ice albedo feedback, of the, you know, the other direction of ice albedo feedback. If a planet starts to get really covered in ice, then it's more reflective, and then that cools it and it gets more covered in ice and more reflective. And in terms of very simple modeling, you can say, well, that's irreversible. It's a state that a planet can get stuck in. And you can show, you know, in terms of the simple mechanics of ice albedo feedback, why a planet could get stuck in that state and never leave. And yet Earth didn't get stuck in that state. And so that you can go from that very simple consideration to, well, why didn't it? Well, the next level is it's more complex, because you have volcanism going off, which is impervious to surface climate. And that, you know, so you have greenhouse gases being fed into the planet. And if everything else stops, which it does in the snowball, then Earth sort of escapes from the snowball, because there are other things going on. But I mean, the remarkable thing is that life did just fine through that. So, you know, you could say, you know, maybe that's not luck. Maybe there's something about a global biosphere, which is, and this is, you know, what the people who are fans of the Gaia hypothesis and so forth will argue, that once a biosphere is a deeply ingrained part of a planet, you know, it's really, really hard to snuff out, even on a microbial level. You know, sure, the more complex life is vulnerable, and that the tree of life or the bush of life will get pruned, but the roots are very hard. It's hard to uproot, and then the branches sort of grow back. So that can be, you can look at it as like, oh, we're lucky and it's amazing that we're still here. Or you can say, well, it's not luck. Life is just really, really robust. And once you have a global biosphere established, there's almost nothing that can wipe it out.
That's really interesting, but I think that you know, getting back to the issue of climate change, that's something we might be able to build on as far as people helping understand. I mean, there's this principle in biology that if you want to understand the health of an ecosystem, you look at the apex predator, because the apex predator depends on everything below it. And so if the apex predator is healthy, then that says good things about the ecosystem. Well, we are the apex predator, we're the super predator, and so it reveals, you know, how vulnerable we as a species are, because we're so reliant on all these other species. And so, you know, maybe if there is an event that wipes out 90% and there's 10% that survives, we're probably not amongst that 10%. You know, being a former resident of Tucson, Arizona, where the cockroaches are, you know, control the land, you know, it reinforces this issue of just how sensitive we are to the climate around it.
I see Leo has his hand.
Oh, Leo, go ahead, and Joel does too. So please go ahead. Leo, go first.
Thanks also for answering this question, and there is so much information. I just wanted to point out again that you said, okay, life is so hard to get rid of essentially once you have it. But I think it's really important in this context to discriminate between life and complex life. Yes. There has been this book, Rare Earth, that you probably know the people, Peter Ward and Donald Brownlee. And they claim that life in some form might exist almost everywhere somehow, because as you say, it could be so hard to wipe out. but complex life requires so much more, and that is the thing that we try to preserve, right? And that, I mean, there's also this picture of the Earth evolution as a clock, and you see whatever, the Homo sapiens only appeared, I don't know, a few seconds before 12 o'clock, right? And so life has always been there, and indeed been very robust to all these things, but complex life requires much, much more.
Yeah, that's right. That's right. The robustness is of the biosphere, but there's a fragility, a potential fragility to, and not just complex life, but especially, as we talked about before, a civilization that sort of made itself dependent upon a very narrow range of conditions. It's sort of the opposite of, the microbial biosphere can roll with almost anything you can throw at it, because it can have an incredibly wide range of conditions. We're at the opposite end of that spectrum, where we've hitched ourselves to this very, very narrow range of conditions.
Joel, you had your hand up as well, so I wanted to give you a chance to speak.
Thanks. David, one of the things that really impressed me with your talk was the number of graphs that you presented, so this is what you show to public, right? And I guess, based on my limited experience with public outreach, I always kind of tend to shy away from showing graphs, fearing that I'll lose the audience or something like that. But while this discussion is going on, I was thinking about that point, and I had sort of a different perspective come into my mind about maybe that actually kind of gives more of an authenticity to the message. Maybe I'd be curious, sort of what your thoughts are on that, and how you approach, showing such kind of detailed scientific content.
Yeah, I mean, it's a balance, right? You don't want to sort of blind them with science and make them think, oh my God, I walked into the wrong room. But at the same time, I think people appreciate authenticity and respect. You don't want to talk down to them. And so it's just a matter of contextualizing. I mean, I wouldn't give a public talk that was like graph after graph after graph. So I like to mix it up, and I'll show some beautiful planetary pictures, or, tell a joke or whatever, and try to, keep it interesting. But I don't shy away from showing a graph or two if I think it's effective. And the thing to do is explain it clearly. And, I mean, remember that these are not all people. In fact, many of them are not people that are used to looking at graphs the way we are. And so you've got to sort of stop and say, okay, so what does this mean? Well, down here, this is time. And so like, this is like, when the Earth was young, and this, take a little time and sort of try to really make sure that you're showing that you're not assuming that people are just comfortable reading graphs. But at the same time, I think people appreciate being sort of led into your world. It's like, this is how we think. This is why we think this. And these squiggly lines actually help us to go through the argument. So I think you have to sort of be artful and choose them well, and then make sure you explain them well. And if you do it right, then you're sort of showing them respect. It's like, you guys are capable of following this as long as I explain it clearly. And here I'm letting you into our world. It's a little bit like, and this is probably even a little bit stranger, more controversial, but I think I showed you the one in my meta talk where I showed a couple of equations, and I said, I don't expect you to like understand that this, it was like the T to the fourth equals energy, whatever. But I'm just showing you one of these because I want you to understand that we use these, and this is the basis for why we think we know something. And there's certain things that these equations really work well for, and we can know the answer exactly. If you simplify the problem to just a reflective sphere in space and say, how hot's it going to be if it's got this much reflectivity, it's this far from a star, that we know the answer exactly to. And then there are aspects of the problem that we don't know the answer exactly to. But, so sort of using that to show the character of how we think about things, even if you're not leading them through the entire argument, and sort of letting them in on how we think, I think can be helpful.
So related to that, Adrian had the question of, do you have a recorded version of your public talk? You've given us the meta version. Do you have one that people can go watch online?
Yeah, let me think about that. I mean, because there's one that they made a pretty good tape of that was at Case Western University that is on YouTube, and it's gotten a lot of hits. I'm just trying to think, because that was about 10 years ago. And I mean, the talk is pretty similar, but I'm just trying to think there's probably a more recent one that I can come up with. But if I send you the links, Travis, can you?
Yeah,
how should
you can just send me the link and we'll circulate it. Yeah.
Yeah, because that one from Case Western, it's called Climate Catastrophes in the Solar System, and it's pretty good. I mean, I think that one is decent, a good example of this. I'm just trying to think. I know I've given more recent versions of the talk. I'm just trying to think of which ones are sort of recorded and online. But I'll definitely send you that one, and if I think of a more recent one, I'll send that one as well.
Okay. Well, and Dave, I know you need to go in a few minutes, so I wanted to use your last few minutes with us. Can you, of course, everyone's been asking you about phosphine in the atmosphere of Venus. And so the question is, if that detection of phosphine is valid, and there's still some uncertainty in that, what do you make of it? What do you think this tells us?
Well, so that first if is important. And, you guys are, some of you at least are observational astronomers, and I'm not. And so I can't completely judge the veracity of the actual detection. And I think that's something that's being looked at, and it's a difficult observation. And I think that, that's going to be, people are going to be trying to confirm that. But let's skirt that and say, so if it's really there, if it's phosphine on Venus, it's really exciting and interesting, because it definitely means there's chemistry there going on that we don't understand. Personally, I've been an advocate for a long time of the possibility of a habitable zone in the clouds, because the conditions are moderate. There are the right elements. There are energy flows. It would have to be a kind of life that can deal with strong acid. But I don't completely rule that out. But of course, if there's phosphine, we can't jump to, there's life, but we can jump to, there's some chemistry going on that we don't understand, and we need to understand it, because this is how these gaseous biosignatures, this is how we've proposed to find signs of life on exoplanets. So this is an opportunity. Here we found something that at least superficially looks like that on the planet next door. And unlike exoplanets, we can send a mission there and find out what's really going on, which, we'll never be able to, well, not never, but basically never, for practical purposes, be able to do that with an exoplanet. So it's an opportunity to test out this atmospheric biosignature way of thinking, and either discover some, unknown, maybe it's catalysis on aerosols, or, I'm not jumping to life until we rule out a lot of other things. But right now, if it's there, it's a genuine mystery. There's no easy way to make the phosphine in the atmosphere. So one way or another, it'll teach us something really important.
That's great. Well, it has been an hour, and Dave, I know you have other things that you need to run to. So thank you so much for participating. This has been awesome. I have really enjoyed all the answers. And thank you, everyone who attended today, for your awesome questions. I know we could easily go another hour or two. There's so much to talk about. But just for those, let everyone know, we are recording this, and we will be posting this on YouTube. So this will be saved for posterity. So
thanks, Travis, and thanks everybody. And by the way, if feel free to reach out if there's follow-up that we didn't have time for. I'm easy to find.
So Dave's a member of A4E, and so I'm sure he'll be more than happy to answer any follow-up questions you have. I will mention in the chat, looks like someone has found Chris has already found one of your YouTube videos, but if you do have a more recent one, because obviously 10 years, a lot can change in science, and so it'd be great to have one of your last talks. So thank you all for attending. Thank you, Dave. This has been wonderful, and look forward to talking with you all again soon.
If you're interested in Astronomers for Planet Earth, you can learn more at our website, astronomersforplanet.earth, and on social media as well. If you would like to be notified about future talks and events, please follow and join us.